So now in this lecture we are going to discuss the compound pendulum, right? Compound pendulum. Compound pendulum, right? What is the compound pendulum? If a rigid body, suppose this is a rigid body, right? This is the rigid body like this, right? This is the rigid body, and there is a horizontal axis. This axis is horizontal and passing through this point, right? Like this, and its center of mass is over here. Suppose this is the rigid body, right? And it is hanging like this, right? This is the rigid body, this is the horizontal axis. If you give a small displacement, then it will start oscillating like this, right? So then this type of the system is called the compound pendulum, right? This is the horizontal axis, horizontal axis, right? And this is the rigid body, right? When the rigid body is suspended from the horizontal axis, so in equilibrium, it will be the center of mass, and therefore in equilibrium the mg will act in this way, and the net force, the normal, will be acting in this way. Are you getting or not? So it is in equilibrium, rigid body is in equilibrium, you can say equilibrium, right? And this system is called the compound pendulum. Are you getting or not? So for this compound pendulum we have to find, the time period of oscillation, right? So to find the time period of oscillation, what we have to do, we have to displace a little bit, right? Like this. If you displace the body, right, this is the horizontal axis, suppose this is the horizontal axis, suppose, and this is the point of suspension, is the center of mass. The distance between, what is L is the distance between, right, distance between center of mass and point of suspension, point of suspension, right? When you give a small angular displacement, this body is displaced a little, right? Its center of mass come over here, right? This is the horizontal axis. If you give the small angular displacement in this direction, so this is the mg. All right. So now if you think about this, the small angular displacement is this, about this, right? You have to find the net torque. What is the net torque? The restoring torque. It will perform the angular SHM, right? Like this, right? So what is the net torque about O? Net torque about O. What is the net torque? Say force, this is the force and perpendicular distance, right? And what is the direction of the torque? It will be the direction of the torque, right? So is equal to mg into perpendicular distance. If this is theta, this is also theta. So in this triangle, sin theta is what? You will write perpendicular upon hypotenuse. So d is equal to, you may write L sin theta. And the theta is small. Therefore, sin theta is approximately, you may write it as the theta. So the net torque is equal to mg into d, and d is L sin theta. All right. Listen one thing. The angular displacement is in this direction. This is the angular displacement. So the direction of angular displacement is out of the board, right? While the torque is acting into the board, right? So if moment of inertia of this rigid body is I, about this point I, so net torque is equal to minus I into alpha, you can write in this way, right? So alpha is equal to mgl upon I, and this sin theta may be written as into small angle theta, right? And this minus is come this side. So this is the angular acceleration. What is this? Angular acceleration. Therefore angular acceleration is alpha. What is I? You may write I is the moment of inertia of rigid body, about horizontal axis passing through O. Horizontal axis passing through O. O. All right, passing through O. You may write passing through O. Right. This is the moment of inertia of the body about this axis of rotation. Right. Angular displacement is anti-clockwise sense and the torque is clockwise sense. Therefore, net torque, when you will find the net torque, you will put it equal to minus into alpha. And this is the angular acceleration. Alpha is equal to mgl upon I minus theta. Since here, you may write here, since alpha is proportional to minus theta. This is the angular acceleration, and this is what? Angular displacement, right? So therefore, motion is what? Motion is angular SHM. Angular SHM. The angular SHM and the linear SHM is the same thing, though no big difference. Only in this case, the standard equation of the angular SHM will be omega square minus theta. Right? Alpha is equal to, in the linear SHM, the linear acceleration is equal to omega square minus x. Here, this is the linear displacement, it is the linear acceleration. In this case, this is the angular acceleration and the angular displacement. This is the standard equation of angular SHM, and we have found for this compound pendulum alpha in this way. You can compare omega square is equal to what? This is equal to mgl upon I, right? Implies that omega is equal to root mgl upon I. It may be written as 2 pi by t is equal to root over mgl upon I, right? T is equal to 2 pi root I upon mgl, right? This is the time period of oscillation. I is the moment of inertia about this axis of rotation, and L is the distance between center of mass and the point of suspension. Is it clear or not, you tell? Sometimes if the body is given like this and this is the center of mass, right, about this axis, if the moment of inertia is what? About this axis is ICM, right, and about this axis is I, and this is the perpendicular distance L. So this is the axis of rotation passing through center of mass. This is the axis of rotation passing through the point of suspension O. So you can apply these are the two parallel axes. To find this moment of inertia, I may be written as ICM plus m into L square, right? This is the parallel axis theorem, right? By parallel axis theorem, you can write the moment of inertia, this I is equal to ICM plus ml square, right? Copy this. So this is the time period of the oscillation for this compound pendulum, right? And the I is the moment of inertia about this point of suspension, right? So this may be written as the time period, the moment of inertia is what? ICM. After this, you can write ICM plus ml square. What is the ICM? Is the moment of inertia passing through the center of mass. If the radius of gyration, what is k? ICM is equal to m into k square, right? Where what is the k? The k is equal to radius of gyration about center of mass, Is it clear or not? So this ICM may be written as m into k square, m into L square into I. So this time period of oscillation may be written as what? 2 pi root mk square plus ml square, plus ml square divided by mg into L, right? Mm will cancel out, so it may be written as k square plus L square upon g into L, and the time period may be written as 2 pi root, right? If you divide k square upon L square, right, divided by L, so it will be L plus k square upon L. So it may be written as L plus k square upon L divided by G. So if you compare with the simple pendulum, right, so it will be L effective. So the effective length of this compound pendulum may be written as L plus K square upon L. Is it clear or not? So therefore the time period may be written as T is equal to L effective divided by G. Right, where the L effective is L plus K square upon L. L is the distance between the point of suspension and the center of mass. And what is the K? K is the radius of gyration about the center of mass. Is it clear or not? Copy this. So if you make the graph between the L effective, this is the L effective and it depends upon the L, right? If you draw the graph between the L effective and this L, wait for 1 minute, L effect time period and if you draw the graph between the time period, right, the time period and this length L, right, this length L, since time period depends upon what? L upon L plus K square upon like this, right? So T is equal to 2 pi root L upon K square upon L, right, divided by G. If length is 0 mean if the center of mass is present of this point of suspension, what will be the time period? You can tell K square upon 0 and it 1 upon 0 it become infinity, right? So time period is infinity. If length is very high and it tending to infinity, so infinity plus 0 again it become infinity. So time period is a function of this length L, right? As the length is changing, the time period is changing. At length is 0, right, length is 0, the time period is 0. At length is infinity, time period is infinity, right? What is this is the effective length, right? This is the effective length. The time period is infinity for L is equal to 0. If you put 0, the L effective is 0, L effective is infinity. So what is the minimum time period? You tell. The minimum time period can be found if we found the minimum value of L effective. If this L effective is minimum, the time period will be minimum. So this effective length depends upon what? L. Listen, this side I am writing. This is the function you may write. L effective is L plus K square upon L. So this L effective depends upon what? It depends upon L. So to find the minimum value of L effective, you have to differentiate, right? You have to differentiate L effective. If you differentiate this with respect to L, so its differentiation is 1 plus K square. What is the differentiation of L? Minus 1 upon L square. Is it clear or not, you tell? So put it equal to 0, then 1 minus K square upon L square is equal to 0. So K square upon L square is equal to 1, right? And K square is equal to L square, K is equal to L, right? Or L is equal to K. That is for minimum, for minimum value of L effective, right? For minimum value of L effective. You tell me, what should be the value of L? The L value, the small L value must be equal to K. That is, this value must be equal to K for effective length, minimum value of effective length. And what is the minimum value? What is the effective length minimum value? It is minimum when L is equal to K. So K plus K square upon K is equal to 2K. So the minimum value of effective length is equal to 2K, where K is the radius of gyration, right? So if you draw the graph between the time period of oscillation and as a function of length L, the graph comes like this, right? At L is equal to 0, it is infinity. At infinity, it is infinity. At L is equal to when the length between point of suspension and center of mass become equal to radius of gyration about center of mass. The time period is minimum, and this minimum time period is 2 pi root L effective minimum divided by G. And this is what is the minimum value of the L effective? Say it is 2k by G, right? So what is the minimum value of time period is over here at L is equal to k. This is 2 pi root 2k upon G, right? This is the minimum time period of oscillation for this compound pendulum. All right, copy this. So now let's see some example. Suppose this is a rod, right? The rod of length L, mass M is suspended from its one end like this, right? Suppose this is the rod and it is suspended like this. If it is tilted little bit by angular theta, so it will start oscillating like this, right? So we have to find the time period of this rod about this axis of rotation. Is it clear or not? If you give the angular displacement little bit like this, so torque will be applied this and it will start oscillating about its mean position, right, to and fro. Are you getting? So if this is the center of mass, you can consider, right? What is the distance between the point of suspension and the center of mass? It is L by 2. Fine. So what is the time period formula you tell? It is 2 pi root 2 pi root what is the formula? I upon mgl. You will write in this way. The formula for the time period of compound pendulum you will remember in this way, right? Otherwise it is little tough to remember in other form. I is the moment of inertia about this axis. L is the distance between center of mass and point of suspension. So here the L is, what is the moment of inertia of this rod? Tell me about this axis of rotation, about one end. Did you remember? ml square by 3, right? And this length L is L by 2. So I am writing the moment of inertia is ml square by 3 divided by mg in place of L, right? What will you put? Say L by 2. You have to remember this thing. So this is 2 upon 3 L by G is the time period of oscillation for this rod. Is it clear? Copy this. So let's see another example. If the same rod is suspended, right? This is the rod, the mass M, length L, and now it is suspended from one end, and this distance is L by 3, suppose. All right. So, and this is the horizontal axis like this, and it is rotating about the horizontal in this way, right? Can you find the time period of this simple pendulum, right? Copy this. So let me try this. Suppose this is the point of suspension, this is the center of mass. The distance between them is L dash is L by 2. This is complete distance is L by 2 minus L by 3. So it is 3L minus 2L upon 6 is equal to L by 6. So this is the L dash. And what about the moment of inertia about this? I is equal to ICM plus M into T square. The center of mass, the moment of inertia about the center of mass is ml square by 12 plus m into this distance is what? Say L by 6 whole square plus ml square 36, right? Chaching 36, so 3 ml square plus ml square 4 ml square upon 9. So the moment of inertia is ml square upon 9. Is it clear or not? Now you can write down the time period is equal to 2 pi root L upon, I upon mgl. So what is the moment of inertia about this axis we have found? It is ml square upon 9 divided by mg. And what is L? L is L dash over here. This is L by 6. So in this way you have to solve this question. This is 2 pi root, right? This is 6 upon 9 L upon G, and this is equal to 2 pi root, right? 2 upon 3 L upon G is the correct answer, right? So in this way, about the point of suspension, you find the moment of inertia, you find the distance between center of mass and the point of suspension, L dash, assumed to be L dash, and here it is L by 6. Put in the formula, you will get the answer, right? Copy this. So for example, we can take a one more illustration. Suppose this is the disk, right? This is the disk. This is the disk of mass M and radius R, right? It is the center of mass and it is suspended about this. This is the point of suspension, the horizontal axis, right? You may represent like this, right? This is the horizontal axis of rotation and it is displaced a little bit, right? Initially at the equilibrium, the disk will be like this and it is displaced little bit. You have to find if, right, disk is displaced, right, by a small angle theta, find its time period of oscillation. I think you can do this. How? You tell. What the formula you are going to apply? T is equal to 2 pi root I upon mgl. What is I? I is the moment of inertia about this point of suspension, and this is the two parallel axes, and L is the distance between the center of mass and the point of suspension. So T is equal to what? 2 pi root. Yes, mg. What is the distance between this? Say it is equal to R. What is the moment of inertia? How to find the moment of inertia about disk? This moment of inertia is what? Center of mass, 1 upon mr square, if you remember. This is the another axis. This is the one axis. This is the another axis. The two parallel axes. So what is the I? Is equal to ICM plus m into d square. So the I will be equal to ICM plus m into d square. The ICM of the disk is half mr square, and the d, right? What is this separation? D is equal to capital R, right? So this is equal to 3 by 2 mr square is the moment of inertia about this axis. You understand? So now you can put the value. What is the I? Is equal to 3 by 2 mr square. What is the answer? 2 pi 3 by 2. This is 3 by 2 R upon G is the time period of oscillation, right? Copy this and try the next question. Suppose this is the disk and this is the center of mass. It is suspended from the midpoint. Suppose this distance is R by 2, right? This is the axis of rotation, right? And you have to find the time period of oscillation about this axis of rotation, right? Copy this. So let's see what will be the answer. 2 pi root I upon mgl. So what is the moment of inertia about this? ICM. This is the disk. Again, you may write this is the disk of mass m, radius r. The I is equal to ICM plus m into d square. Fine. The ICM is mr square by 2 divided by plus mr by 2 whole square. So when you will simplify, this is mr square by 4. Take the 4 LCM, 2 mr square plus mr square. It is equal to 3 by 4. Mr square is the moment of inertia about point of suspension. And what is L? L is the distance between the point of suspension axis and the center of mass axis. So now you may write T is equal to 2 pi 3 by 4 mr square, right? This is 3 by 4 mr square mg, and this is r by 2. So 2 pi root 3 by 2, when you simplify, r upon g is the correct answer. Are you getting or not? Is it the same answer you are getting, Varsha? Yes, copy this. For example, if this is the ring, this question is asked many times, although it is very simple, right? This is the ring of mass m and radius r. The horizontal axis is like this, right? So now it is displaced little bit. This is the axis, right? This is the axis of rotation, you can say, right? And you have to find time period of oscillation, about axis, about horizontal axis, right? A dash. This is A, this is A dash, right? If it is displaced little bit, right? Find the answer. So how to solve this question? The same formula I will apply again and again. 2 pi root I upon mgl. This is the center of mass axis. This is the point of suspension. The distance between them is what? Equal to r. So it is equal to r. And what is the moment of inertia about this axis? If this is the ring, no, mr square is the moment of inertia about center of mass. And we have to find, this is the ICM. Please check ICM, and this is the I, right? So I is equal to ICM plus MD square. So about this axis, ICM is what? Say MR square. And what is the D? Separation between them, R. So the I about this axis, the moment of inertia is 2mr square. I think you are getting correct answer. This is mr square. So T is equal to 2 pi root 2r upon G is the correct answer. Fine. Copy this. So read this question. A rod, in this illustration, the rod with rectangular cross section. Suppose this is the rod. The cross section is rectangular, no doubt, right? The rod is rod, right? The cross section is rectangular little bit, right? Oscillate about axis passing through one end, and this is the axis of rotation like this, all right? And it behave like a second pendulum. When it is given a small displacement, then it oscillate like this. So T is equal to 2 pi root I upon mgl or not? And the time period is what? Say second pendulum mean the time period is 2 seconds. So we have to determine its length, capital L. It is center of mass. What is the I value? I value about this. The I value is ml square by 3 or not, you tell. And what is the L? L is the separation between point of suspension and center of mass. And the L value is what? Say L by 2. So it is equal to ml square by 3 divided by mg into L by 2. Fine. 2 will cancel out. 1 upon pi is equal to square root. This is 2 upon 3 L by G it is. Right. Take the square, 2 by 3 L upon G. All right. So the length is equal to pi 3G upon 2 into pi square. G and pi square are approximately equal. They will cancel. Length is 3 by 2 is equal to 1.5 meter. I think you are getting the solution, right? Copy this. So read this question, right? In this illustration, a rod with rectangular cross section oscillate about an horizontal axis. Suppose this is the rod and the rectangular cross section is over there, right? Like this. This is the rod and this is the horizontal axis, right? It oscillate like this. Is it clear? Passing through the one end, the rod assumed to be the mass m, the length L, this is the center of mass, right? Through one edge, it behave like a second pendulum. If it behave like a second pendulum, then time period is 2 seconds is equal to what? Right? Time period is equal to 2 pi root I upon mgl. All right. Determine its length. Right. Suppose the length of this rod is assumed to be L. Right. It behaves as a second pendulum. So therefore the time will be equal to what? 2 seconds. Now you have to write down the value of I and mgl. What is L? This is the point of suspension and this is the center of mass. L is this distance between the axis of rotation and the center of mass, right? So this is equal to capital L by 2. And what about the moment of inertia about one end? What is the moment of inertia of the rod about one end? Do you know? Yes, about one end moment of inertia is ml square by 3. So put the value of I, this is ml square by 3, mg, and this L is capital L by 2. So then it is 2 will cancel out, 1 upon pi root over 2L. If you simplify, it is 2L upon 3g. 1 upon pi is equal to 2L upon 3g, right? Make it a square. Pi square is equal to 2L upon 3g, right? So what is the value of L? From here, the value of L is equal to 3g upon 2 into pi r square. But the value of g is approximately equal to pi r square. So pi square and g will cancel out. So L will be equal to 3 by 2. It is 1.5 meter. So the length of this rod is equal to 1.5 meter if the time period of this this rod about this axis is 2 seconds. That is, it behave as a second pendulum, right? Copy this. So you can read this question. In this example, right, time period of bar pendulum. Suppose this is the rod, the bar pendulum. What is the bar pendulum? You tell. Bar pendulum is nothing but a rod of mass m, length L. That is the thing only, right? And the time period of this bar pendulum about any axis of rotation, right, is same as we have found. Suppose this is the axis of rotation. What is the time period of oscillation? Is 2 pi root I upon mgl. Is it clear or not? You tell, right? So time period of bar pendulum when suspended at distance 30 centimeter and 50 centimeter, right, from its center of mass come out to be same if the mass of the body is 2 kg, right? So what they are asking, the moment of inertia about the first axis, right? Listen one thing, this is the time period of oscillation, right? The I is nothing but about this axis. What is the moment of inertia about this axis? If this is the center of mass, this is ICM plus m into L square. Is it clear or not? This distance is L. As I told you, the ICM is equal to what? Mk square, ml square. If you put the value of I in this expression, T is equal to 2 pi root mk square, ml square divided by mgl, right? If you simplify, will cancel out, T is equal to 2 pi root and L square upon L plus K square upon L, all right, divided by G is equal to time period. Is it clear or not? You tell, right? So the time period depends upon what? It depends upon the L effective, right? What is the L effective? Is equal to L plus K square upon L. So the time period may be written as L effective upon G. This thing we have covered in the theory, right? Okay, now what is the question? In this question, first, this is the bar pendulum, this is the center of mass. First, it is suspended, right, from the point 1, which is a distance, suppose the L1, all right, and then it is suspended, right, this is the center of mass, about the other point, which is at distance L2. The value of L1 here is 30 centimeter according to question. Suppose this is the point A, this is the point B, right? This is the axis of rotation, right? This is the axis of rotation, this is the axis of rotation. Are you getting or not? Like this. And L2 value is 50 centimeter. Are you getting? So when this pendulum is, right, this is the axis of rotation and it is oscillating. Are you getting? So what will be the time period? The time period will be equal to 2 pi root L1 plus K square upon L1. What is K? K is the radius of gyration about an axis passing through the center of mass. So in this case, what will be the time period? Now in this case, if you change the length, right, the time period is 2 pi root L2 upon K square upon L2 upon G. Is it clear or not? Listen one thing. If you see the time period of this, right, pendulum depends upon the length L, and you have seen the time period T and the length L. What the graph we had discussed, this is the graph, right? So you will see what is the value of the L is equal to K. The L effective is minimum, right? L effective is minimum, and the time period will be equal to minimum. Are you getting or not? And what should be the L effective for minimum value of the T minimum? The L should be equal to K. We had discussed. Is it clear or not? But here in this question, you will see the same time period may be obtained at two different lengths, L1 and L2. One is the less length, one is the more length. At L1, the time period is same, the L2, the time period is same. So therefore, for L1, this is the time period, for L2, this is the time period. According to question, for this length L1 at 30 centimeter, 50 centimeter, both time period are same. If time period are same, then what will we have? L1 plus K square upon L1 upon G must be equal to L2 square plus K square upon L2, right, upon G. Even the length of the axis of rotation from center of mass is different, but time period will be same. Why? Because from this graph you can see for the two length L1 and L2, the time period of this oscillation will be the same, right? If you simplify, 2 pi root G will cancel out. L1 plus K square upon L1 is equal to L2 plus K square upon L2. The L1 is 30 plus K square upon 30. Fine. It is 50 plus K square upon 50, right? You must simplify this. This is K square upon 30 minus K square upon 50 is equal to 50 minus 30. It is equal to 20. If you take K square common, simplify this. It is 20. K square, if you simplify, 20 upon 50 minus 30, 30 into 50. This is 20. So 20 will cancel out, and K square value is what? 500. And the value is in centimeter square. Is it clear or not, Utal? Right. Now, or in meter square, 1500 into 10 ki power minus 4 meter square, because K is the radius of gyration, so its square unit will be meter square. Are you getting or not? Now what they are asking, according to question, they are asking the moment of inertia of the rod about this axis if mass of the rod is 2 kg. So what will be the moment of inertia? This is the ICM, this is the I1 we have to find. So therefore I1 will be equal to ICM plus M into L1 square. What is the ICM, Utal? It is equal to M into K square plus M into L1 square. What is the value of M K square plus L1 square? What is the value of M? It is 2. What is the value of K square in meter square? It is, sorry, you will write it minus 4, 0.15 plus L1. What is the L1? 30 centimeter. It may be written as 0.3 meter. So this is 0.3 whole square. It is 2.15.09. 2 into 4, right, 2. So it is equal to 0.48, right, kilogram meter square is the moment of inertia about the axis passing through this point A, right? So this is the question. I am repeating this once again. What is given in the question? In the question, a bar pendulum is given. The bar pendulum is not a very big different thing. It is a simple a uniform bar, right, of length L, mass M. If it is suspended from this point O, whose distance is L from the center of mass, it oscillates, right, to and fro. Time period is given by this in terms of radius of gyration and length of the rod, right? It may be, it is small l, right? It may be given by this. So the L effective is this. So time period depends upon what? L. So if this is the L, what is L? L is not the length of the rod, rather it is the distance between the axis passing through center of mass and the axis passing through the point of suspension. This is the small l. So if this distance changes, the time period changes, right? This is the time period is a function of small. So if you draw the graph, we have done this, the graph between t and different values of l come like this. This is minimum when L is equal to K, when L effective is minimum, L is equal to K. We have done also this. Now from this graph you will see for the same time period, this is the length L1 and L2, or you can say the one time period will be same for the two different length L1 and L2. In this question, for L1 is 30 centimeter, L2 is 50 centimeter, and time period both are same. So we will calculate, and from here the radius of gyration k square we have found. They are asking the moment of inertia about this axis. So the moment of inertia is I is equal to ICM plus MD square, MK square, ML1 square. When we will calculate, you will get the answer. I think it should be clear, right? Copy this. So read this question. In this question, time period of a small oscillation of bob in arrangement. What is the arrangement? Suppose this is the length L and this angle is 45 and this angle is also 45, although it is not shown in the figure, right? And this is the bob length L. Now this is the bob, it is displaced by little bit and it is oscillating like this, right? So what is the effective length for this? The time period for this will be equal to 2 pi root length effective from the point of suspension of this bob M is equal to Z. So just you have to find the effective length. How this system is, you tell. What is the motion? What type of the motion? It is displaced by this and it oscillating like this. So it will be the H, right? So if this is L, you may apply sine 45 is equal to H by L is equal to 1 upon root is equal to H by L. So the H is equal to L upon root 2. So the time period in this case will be, this is the effective height of the bob from the point of suspension. You can say it is L upon root 2 upon G. The time period is 2 pi root L upon root 2 G, right? So therefore the B option is the correct option, right? Copy this. So read this question. In this illustration, right, a uniform disc of radius r is suspended through a small hole. Suppose this is the disc, uniform disc, this is the center of mass of the disc, and it is suspended from a hole, right? Like this is the axis of rotation and this is the whole axis passing through this, right? Suppose this distance is x and the radius of the disc is smaller, right? Find the minimum possible time of the disc for a small oscillation, right? You can say we have to find this T minimum is equal to I upon mgl, all right? And in the other way it is L effective upon G. Do you know what is L effective? Yes, the effective length is nothing but L upon K square upon L. And for the minimum time period, the effective length should be the minimum. So how to find the minimum length? I think you know this, dl upon dl, it differentiate 1 minus K square upon L square, right? Put it equal to 0, right? K square minus upon L square is equal to 0. So K square is equal to L square, L is equal to K, right? So when this length assumed to be L, this is the point of suspension and this is the center of mass. So for the minimum time interval, that is for the effective length to be minimum, this distance between the point of suspension and the center of mass must be equal to what? Radius of gyration about an axis passing through center of mass, right? So what should be the L? And what about the radius of gyration, you tell? If this is the disc, this is the disc, what is the moment of inertia about center of mass? Is equal to 1 by 2 mr square, put it equal to mk square, will cancel out, K square is equal to R square by 2, K is equal to R by root 2. You understand or not? So this is the value of the radius of gyration. So what should be the height of this point of suspension from center of mass? so that when it displays little bit, it oscillates with minimum time interval. The value of this length must be equal to radius of gyration, and radius of gyration about center of mass is r by root 2. So where should be the hole made? You tell. At what distance the hole should be made? L distance is equal to radius of gyration. So L value is k is equal to r by root 2. Is it clear or not? So L value is what? R by root 2. Now this is the distance of the point of suspension from center of mass to have minimum time period. And what will the minimum time period you tell? For the minimum time period, 2 pi root. What is the L effective in this case? When L is equal to K. So what is the L effective in this case? You tell. The L effective will be equal to L plus K square upon L. It depends upon the L. When L is equal to K, so the effective length will be equal to K square upon K. Although we have done this already. So this is 2K upon G. Where K is the radius of gyration. In this case, it is equal to what? You tell. K value is R by root 2. This is R by root 2 upon G, which is equal to 2 pi R root 2 upon G. Is it clear or not? So this is the minimum time period of the oscillation. When this minimum time period is, if the point of suspension is at distance L is equal to K, is the radius of gyration about the center of mass, right? So this is the question. Copy this.